Yeah, thanks for the introduction. Yeah, and now today I will present our leak tracing algorithm, which is a simple algorithm that combines filterable shadow maps with ray tracing to reproduce pixel-perfect shadow maps in a fraction of the time. For this, we first look at shadow maps. If you are not familiar with them, it's pretty simple. Shadow maps is a two-pass algorithm where first up we capture the depth from the view of the light source, and then this depth information is stored in a shadow map. And then in the second pass, to look up if a point is shadowed or not, we compare the depth value of a reprojected camera point, and if the shadow map depth is smaller, then the point is shadowed, and if not, it is lit. Here in small example. However, shadow maps suffer from some problems. So first up, as the depth information is stored in a texture, it is always bound by the resolution of this texture, and this can cause aliasing on the edges of the shadow when the resolution of the view does not match with the resolution of the texture. Additionally, without any bias, shadow maps produce these nasty artifacts called shadow acne, which happens due to self-shadowing. And to avoid this, you can set a bias value, but if you set it too high, it can happen that the shadow appears to be detached from the object. There are some prior works mainly focusing on solving the aliasing issues, which you can see here. However, all of these techniques are bound to the camera view and require re-rendering the whole shadow structure every frame, and this can be quite expensive for some of them. Another way to solve the aliasing issue is to use percentage closure filtering, where the shadow map test is repeated for nearby samples in the shadow map, and this then results in a smooth shadow, which basically is a probability distribution function of that shadow. However, this always requires multiple texture accesses, which is not always the best thing performance-wise. So we can do better, and that is with filterable shadow maps, where the whole shadow evaluation process is modeled as a probability distribution function. These are also completely free of these shadow acne artifacts, so no bias value needs to be set for them. And they all use different depth vectors to approximate this probability distribution functions. So for example, there are variant shadow maps which store the first two depths, so depth and depth squared. Then there's exponential shadow maps, which store an exponential function to approximate the shadow over an exponential function. Then there's exponential variant shadow maps, which combines both of these techniques. And then there's also moment shadow maps, which store the first four depth moments too, and use the 4 moments problems to approximate the shadow. While all of these can sample a shadow or create a shadow with one sample free of these aliasing artifacts, they all suffer from another problem, and that is light leaks. As you can see here quite well, hopefully. These happen when the penumbra of another shadow basically leaks through the shadow. So in this case, the plant hanging from the street lamp leaks through the shadow of the bush, and this creates this light leaking artifact. Of course, we can always go the easy way and use ray tracing, which is now more accessible due to GPU hardware. So, and this is pretty simple. We just shoot a ray from our point to the light source. If we hit something, point is shadowed. If not, it is lit. And now we get a perfect shadow. Yay, problem solved. Not really. Ray tracing is a bit slower, or not only a bit, like 80% slower than just sampling a value from a depth map. So this is, of course, not optimal. So to increase performance of ray tracing, we would like to shoot way less rays. And as the filterable shadow maps works on most parts of the shadow, why not just combine both and use the filterable shadow map as a template and just trace and ray whenever the shadow map leaks? This translates to trace and ray whenever the shadow map, filterable shadow map test is between 0 and 1. So if the probability is not completely sure that this point is actually in shadow or lit. And with this, we are able to produce pretty good results in only a fraction of the time. So this is only 10% slower than normal variant shadow maps and 60% faster than ray tracing for this example. Here's also a little camera path through the bistro scene. So now my question, did you spot an obvious error? If not, it's here on the Vespa. So there appear some errors, and there's also another one down here, creating these zigzag artifacts, which mainly happen due to discretization of the shadow map, as we still work based on the texture, and rasterization can sometimes miss details, especially if the light is near parallel to the object. With ray tracing, of course, this would not happen. However, these are quite small errors, so to fix them, we opted to use temporal information. And for this, I introduce this very colorful mask to you, where we start basically categorize the shadow result from the last frame, and which we will then use to fix the errors. So first up, we have this black pixels, which is confidently lit, so the shadow map evaluated 1, or we aborted earlier due to shading. Then we have the green case, where the shadow map evaluated 0, so also no ray necessary. We can just shade this, put this pixel in the shadow. This white case is when the shadow map was not confident, and we said if the probability is lower than 0.5, but higher than 0, it is unsure shadowed, so we shot an ray in this case, and the ray had the same result. This is the same, but for the lit case, so the shadow map value was between 0.5 and 1, and we shot a ray, and ray had the same result. And now the problematic case, this purple one, where our shadow map evaluated lit, we shot an ray, but the ray had a different result. And what we mainly want to do, as you probably see, these light errors that are still present are all around this purple case. So we just want to expand this purple case until it's not possible. For this, we look at this small part a little bit more zoomed in. So here on the right side, we have the temporal mask, and on the left side, we have our current results. And currently, we only evaluated the shadow map, so we did not shoot any rays yet. So we only know if our point in this case is confidently lit, or if we are unsure and would shoot a ray. So let's look at this bottom right sample. And the sample looks up in a 2x2 neighboring region in the mask. And we compare each of the results from the mask with our current sample. For this case, it's all unproblematic. The black case, of course, when it's confidently lit, we don't need to change anything. And the red case only confirmed our known result that this point is lit, so it's unproblematic, and we don't need to distribute any more rays. Next up, we look at what happens if a sample falls in an unsure region. Of course, as we already will distribute an ray, we also don't need to test anything else here, so no ray necessary, or no additional test necessary. Ray is already distributed. Now the interesting sample. Now we have one sample, the purple case, where the shadow map result does not match with our current result. So do we actually sure that this is not an error? We expand this ray, and now we trace an ray at this point. So if we would do this for all pixels of our current example, it would look like this. So the array was expanded at the edge. And this is actually quite fast in real time, as you can see. But also, I need to point out that this is basically the worst case, where all geometry in the scene would just plop into existence. Normally, this does not really happen that often. So we would also distribute an array whenever a reprojection fails. So if you move the camera to the left side, the missing information on the left side would be traced to get a good approximation, or to know if this pixel is shadowed or not. And as we already stored this temporal information, we can also use them to eliminate some rays we don't actually need. So maybe you noticed this white case and this red case, they are only confirmations. So we could actually use this temporal information to test if we actually need an array here. So for these both, we also look up our neighboring pixels in the temporal mask, and if they all have the same result, we can say, oh, yeah, it's probably the same result as in the last frame this was shadowed, or either confidently shadowed or was shown by ray that this point is actually shadowed. And this basically happens instantaneously. So next up, we move to some optimization we also apply to our leak tracing to make it even faster. So normally these filterable shadow maps store more than one depth channel, but this can be quite expensive for sampling and storing. But we notice that normal bilinear interpolation is sufficient. Therefore, we can replicate a filterable shadow map using a normal shadow map and using a gather operation. With this gather operation, we get the 4 depths we would normally get for the interpolation. And then we use those 4 depths to basically replicate a filterable shadow map, in this case, the variant shadow map, and then we manually interpolate them. And this would be the same value we would get from linearly sampling the filterable shadow map. This saves memory and also increases performance quite drastically as less bandwidth is used. We can also safely reuse shadow maps, even with camera movements. So for cascaded shadow maps, multiple cascaded levels are used to fill up the view. And these normally need to be re-rendered every frame, because if you don't, you'll see these choppy jumps on the right side. And if you actually re-render them, it's much more smooth, especially with anti-aliasing. However, with our leak tracing, we can actually just reuse the shadow, as we always reproduce the pixel-perfect ray trace shadow. And this drastically reduces time we actually need to generate the shadow map, as it now only needs to be re-rendered every couple of seconds instead of every frame. However, this reuse can only be applied, of course, to static parts, as if we would use this for dynamic parts, the shadow would appear choppy there. So we split the shadow map actually into 2, and the dynamic one is rendered every frame. Of course, as there are often much less dynamic objects in the scene, we still get a huge performance improvement by reusing. And to actually use this, we sample from both shadow maps using the gather operation and then taking the min of all of these gather values, basically reproducing the combined shadow map. And this shadow map is then used in the filterable shadow map test. Here are also some results. So we tested our leak tracing in multiple scenes, and one of which is Emerald Square. And I now show the ray tracing times, which we would get if we would only use ray tracing as you can see, there are some huge spikes. One of the spikes is shown, and this often happens for ray tracing if many alpha tests, if the shadow ray has many alpha tests. And this is actually the case here, as the shadow mainly consists of a tree. It's casted by a tree. With our leak tracing, we are able to be much more stable in time, and especially don't have these huge peaks for alpha tested geometry. And as you see, in the worst case, we are as fast as the normal ray trace shadow. Also, for comparison, I added the default shadow maps. If we would re-render the shadow map every frame, which is actually slower than ray trace shadows, as the scene is quite huge with 10 million triangles. And also moment shadow maps, which store 4 depth values. So just storing 1 depth value is also a huge improvement, as you see. We also tested our leak tracing at grazing angles. So on the right side, you see the shadow map that's actually used to reproduce the shadow. And yeah, you can see no obvious error at first glance. However, if you would actually compare them side by side with the ray trace shadow, you would notice that some shadows actually disappear, as we always use the shadow map as a template. So if we don't have the resolution needed to actually detect a shadow or a lit place, then we cannot reproduce them every time. However, as you can see at the run times, I think even if not perfectly replicating the shadow, this is a pretty good trade-off. So in conclusion, we introduced leak tracing, where we trace an array whenever the shadow map leaks. And this speeds up the array shadow test by 20 to 80% on average. And it is very easy to implement, as it works on top of default shadow maps, which are already existent in most systems. And also there's no parameter tweaking for different scenes, which is also a problem you have with shadow maps. We have full source code, a demo, and additional resources available at our GitHub. And I thank you very much for your attention.